Hello everyone, I'm Bob Yantoska from the GEOS-Chem support team, and I would like to welcome you to our Getting Started with GEOS-Chem tutorial video. This will be a high-level introduction to GEOS-Chem. We hope to provide you with more videos that will demo how to get set up with and get running with GEOS-Chem in the very near future. So let's get started. So first I'd like to start out by taking a look at what I like to call the GEOS-Chem ecosystem. As you are aware, GEOS-Chem is a model of atmospheric chemistry and composition, but is really more than that. It is one model that can be run in several different implementations. Most GEOS-Chem users typically run GEOS-Chem Classic as it is the simplest implementation. All you really need is a set of compilers, a NetCDF installation, and a computer cluster or cloud instance, and you're off and running. Users who need more computational power can choose to run GCHP instead of GEOS-Chem Classic so they can take advantage of hundreds or thousands of computational cores. GEOS-Chem also serves as the chemical module in several Earth system models, such as the NASA GEOS-ESM, CESM from NCAR, WRF, and most recently the Beijing Climate Center model. GEOS-Chem is also a core component in analytical inversion frameworks such as the integrated methane inversion workflow, and also in data assimilation frameworks such as Cheerio. So there are many ways that you can use GEOS-Chem. The most important takeaway is that whichever GEOS-Chem implementation you use, it all uses the same underlying science code. This ensures that state-of-the-science updates developed by GEOS-Chem users can flow seamlessly into Earth system models, inversion frameworks, and data assimilation systems. And so this all begs the question, which implementation of GEOS-Chem should you use? There is no one correct answer, as this typically depends on the science that you're trying to do. Most new users of GEOS-Chem start out with GEOS-Chem Classic, as it is easy to set up and can be applied to different research problems. But if you're doing something that is very computationally intensive, such as aerosol microphysics, or if you're working at extremely high spatial resolution, or doing both, for example, you might find that GCHP is a better fit for you because you can take advantage of more computational cores than you can with GEOS-Chem Classic. If you're working on climate feedbacks or climate chemistry feedbacks, then GEOS-Chem in either CESM or WRF may be appropriate for your research. So it really depends what you're trying to do. In this tutorial, we're going to focus on GEOS-Chem Classic, as is a good entry point for most new GEOS-Chem users. But first, we'll take a little bit of a look at where you as a new user can find more information about GEOS-Chem. So info for new users of GEOS-Chem. If you're a new user of GEOS-Chem, we recommend that you take a look at the GEOS-Chem website as your first stop. The website can be reached at these URLs here, geos-chem.org or geoschem.github.io. You'll find a wealth of information here, listed at right, such as information about the organizational structure of GEOS-Chem, links to publications and documentation, and information about upcoming and past GEOS-Chem meetings. I'd like to take a pause from the slide deck to show you some of the features of the website. So we'll slide over here to the next desktop. So this is the front page of GEOS-Chem where you landed. Looks like the slide that we had on the previous on the slide deck. You'll see a link to past releases of GEOS-Chem, this will be all the past versions that have been released, and you can take a deep dive onto that. There are future releases that are coming up, such as what's in progress. This is what the GEOS-Chem support team is working on, and so forth. And the current release, which is GEOS-Chem 14.6.0, which we'll look at a little bit later. There's also links to the organizational structures of GEOS-Chem, so you can find information about the steering committee, the working groups, the support team. There's a nice welcome letter for new users that has some links that you can check out. There is information about the support team. These are the folks like myself, Melissa, Lizzie, and Bill who are managing the GEOS-Chem model and maintaining it for the users. There's a list of publications. We keep this on Google Scholar that you can check out. These are all recent papers going back. You can see the first one goes back to 2001, so there's 20 plus years of papers on here. And going back to the GEOS-Chem website, there's a nice narrative description. So if you're writing a paper and you're using GEOS-Chem and you need to put a description about GEOS-Chem into your paper, there's a list of, you'll find information here like a list of the original or historical references, and it talks about each of these different areas of GEOS-Chem, like meteorological fields. You can pretty much copy and paste this text, boilerplate text, into your paper and maybe tweak it up a little bit for your description of the GEOS-Chem model. So that's a really neat thing. But what I like best on the page is our GEOS-Chem user map. So this is an interactive map. Each one of these points is an institution where someone is using GEOS-Chem, and you can scroll in on the map with using I'm using a mouse, so you can use the mouse wheel. You can also use touchpad gestures to scroll in. So for example, here over the UK, you see these are all the user groups. If I click on one of these pins, in some cases there are more than one user groups at a given institution, and they're listed here, so you can take a look at that. The user groups are color-coded, or I should say the pins on the map are color-coded by red is where the support team lives, so that's both at Harvard and Boston or Cambridge, Mass, and also at WashU and St. Louis. Steering committee members are in green, and user groups are in blue. And you can see we have quite a few users, and there's particularly a heavy usage of GEOS-Chem in China and in Asia. So a big shout out to those of you who are going to be going to the GEOS-Chem user meeting in May of 2025. Sorry I can't be there, but maybe another time. So with this information, also there's information about upcoming meetings. There's a meeting in Europe, the GEOS-Chem Europe meeting in 2025. There's also the meeting in, wrong tab. There's a meeting in the Asia meeting at Newest, also in May of this year, and so forth. So there's really a wealth of information. There's links to the documentations. There's all this stuff here that you could check out. So we'll go back to the slide deck and we'll continue on. Okay, so the next resource that you can look at is our GEOS-Chem wiki. So this can be reached at wiki.geoschem.org. So each GEOS-Chem version has its own wiki page, such as for version 14.6.0, which is the current release at the time that I'm making this video. While the website contains mostly high-level information, the wiki contains more technical information and perhaps more specific information about GEOS-Chem versions, such as the benchmarks that we use to evaluate each version and the current status of model development. Since GEOS-Chem 14.0.0, we have migrated all of the software documentation to Read the Docs. Read the Docs is a standard source code documentation platform that's used by most open source software packages. And as you can see here, we're listing a bunch of our manuals for GEOS-Chem and related software packages. So GEOS-Chem Classic, as I mentioned, GCHP has its own manual. HEMCO, which is the emissions package that we'll talk about in a little bit, and so forth and so on. So you can click on each of these Read the Docs packages to get more information about the specific software package. But most relevant to this tutorial is GEOS-Chem Classic and HEMCO, which we'll be focusing on later. One of the really great features of Read the Docs is that it allows us to generate version-controlled documentation. This documentation is stored alongside the source code and is under Git version control. So that means we can publish a new version of the documentation every time we release a new version of GEOS-Chem Classic, GCHP, HEMCO, GCPI, etc. By clicking on this window, when you go to a Read the Docs page, you'll see down here at the bottom right, there's a window down here. It says Stable. You can click on that actually, and it will pop open a menu where you can go to other versions. So Stable always points to the the most recent version, which in this case is GEOS-Chem 14.6. But as you can see, there's 14.5.3. There's previous versions going back to 14.00, which is when the first version that we migrated to read the docs. So if you're using an older version of GEOS-Chem, you can go back to that version and get that version-specific documentation. We can now take a quick look at some of the features of Read the Docs on the next screen. So I'm going to slide over to the next desktop and then pop open the Read the Docs. And it looks like this. We have one for GEOS-Chem Classic. We have one for HEMCO. They all look like a consistent format here. For GEOS-Chem, or GEOS-Chem Classic, you see at the top there's information, the latest release, when it was released, is the Read the Docs broken, and so forth. There's a bunch of information here. The Quick Start Guide, which we'll mention a little bit later, is a good place to learn how to download and run GEOS-Chem. We have information about what hardware and software requirements you need, and these are in manual pages to tell you how to download the source code, download input data, and so forth and so on. So really take a good look at Read the Docs. It will explain a lot of what you need to know to run the model. New in 14.6, we've added these pages called GEOS-Chem Simulations. So for example, if I click on Full Chem Simulation, here we go. If I click on Full Chem Simulation, it takes me to a page and explains all the different options, and it has a list of the species by the given option. So for the standard simulation, these are all the species that are in that simulation, and so forth. And I can go back. On the sidebar, you can click to get a sub-menu if I'm interested in TOMAS, like the microphysics. So in addition to all the standard species above, you have these species, and these are the molecular weights and so forth. So really have a lot of information here. And in addition, there's supplemental guides. These are things that are additional information that you might need to know about using GEOS-Chem. So for example, if you need to build software like your NetCDF libraries, we have a guide how to build software with SPAC. There's a guide on understanding what error messages mean. So this is good information. If your GEOS-Chem run dies with an error, you can go to this page, and we have some of the most common error messages listed here. So, for example, there's compile time errors, there's runtime errors, and you get a bunch of information about the different types of errors. Here's some debugging tips, and there's a bunch of quick tips that you can do to debug your code. There's information about running nested grid simulations. Many of you are running nested grid simulations, the regional simulations over Asia or over North America, so forth. There's information about how to deal with NetCDF files. If you need to manipulate NetCDF files, a wealth of information here. So really, and also there's, I believe up here in Run Your Simulation, if your simulation is running slow, you'll find information here about how to speed it up. So it's a bunch of suggestions that you can do. So really, I would recommend taking a deep dive into the Read the Docs pages because you'll find a lot of information that is useful for you. Okay, so back to the slide deck. So that rounds out the resources about GEOS-Chem. So now I'd like to take a little bit more of a look of using GEOS-Chem Classic specifically. So let's delve into the details of getting started with GEOS-Chem Classic. So what is GEOS-Chem Classic? GEOS-Chem Classic, as I mentioned before, we have the ecosystem of GEOS-Chem, and there are many implementations. GEOS-Chem Classic is the simplest implementation of GEOS-Chem in terms of getting started, getting it set up, and getting running. So it's compatible with the GNU and Intel compilers. So these are two of the more popular compilers that are used in high-performance computing. GNU pretty much comes with every version of Linux. Intel is now, I believe, free and open source. It wasn't before. You used to have to buy the site license for Intel, but the Intel One API compilers are now free. GEOS-Chem Classic can be run on a computer cluster, such as if you're at a university or similar institution like NASA or NOAA or whatever. Or you can run it, if you don't have access to a computer cluster, you can run it on Amazon's cloud computing platform. And so You can take a look, as I showed before, we have hardware and software requirements as we just looked at, read the docs page before. So you can take a look and see what you need on your specific system to get running with GEOS-Chem Classic. GEOS-Chem Classic is parallelized, but it uses a type of parallelization called OpenMP, which I won't go into the details here. So this is a way of running GEOS-Chem using more than one computational core, but this specific type of parallelization limits GEOS-Chem Classic to using a single computational node, which most computational nodes nowadays are typically 100 or less cores. I think the Intel Sapphire ones now are 112 cores. Cascade Lakes are about 48 cores and so forth. So they're of order 50 to 100 cores. So that means that you can't run GEOS-Chem on more than that number of cores, which is a trade-off it's a trade-off that you make for the maybe run on less cores, but maybe GEOS-Chem Classic is easier to get started with. So why should you use GEOS-Chem Classic? Well, as we mentioned before, GEOS-Chem Classic is a good entry point for new users, and it really, especially if you're new to programming or computational modeling. So as I mentioned before, GEOS-Chem Classic can really be easily set up. All you really need is the compiler and the netcdf library, and you're ready, pretty much good to go. Some of the other implementations of GEOS-Chem, you need other specific libraries like ESMF or Maple and MPI, and those can be harder to get started with if you're a new user. So GEOS-Chem Classic is attractive and a good entry point for new users. And most users, if you're a graduate student, postdoc, or early career researcher, you're going to be wanting to spend most of your time on your science rather than on your computing. And so GEOS-Chem Classic makes it really easy to develop and test new science updates. So instead of worrying about debugging something complex with MPI or getting your code running on a 100 or 1,000 cores like with GCHP or GEOS-Chem in CESM, you can really focus on your science, develop it in GEOS-Chem Classic first, and then once it's mature, as I mentioned before, any new science updates that you add to GEOS-Chem Classic, and if these get propagated to the standard versions, these will flow seamlessly into the other instances of GEOS-Chem, such as GCHP, GEOS-Chem, and CESM, etc. So you can develop on a very simple framework using GEOS-Chem Classic, but then your science will find itself maybe one day running in a big Earth system model. And we took a look at on the Read the Docs I mentioned, there's a quick start guide. This is really the best place to get started with GEOS-Chem. It'll walk you through the installation of GEOS-Chem Classic. The workflow here is shown at right, so you'll clone GEOS-Chem Classic from GitHub. You'll create a run directory, load libraries into your environment. You may have to build the libraries if they're not there already. You'll select the simulation options you want to use, configure, build, compile, download the data if you need to, and then start your simulation. So it goes into gory detail about all those steps. So you can just walk through that. We also, on the Read the Docs, there's a folder tree that shows kind of the directory layout, so you can take a look at this. I will say most GEOS-Chem science code is stored in the GEOS core folder, so it would be source GEOS-Chem, GEOS core. The main program is in this interfaces GC Classic folder. Any chemical mechanism code is in this KPP folder. Run directory creation scripts is in this run GC Classic folder, and the HEMCO emissions code, which we'll talk about in a little bit, is in source HEMCO. So I would recommend taking a look at the folder tree, and you can see the different directories. GEOS-Chem Classic supports several different simulations, which are categorized as follows. First, there are simulations where the chemical mechanism has been built with KPP, the kinetic preprocessor. These simulations are the full chemistry simulation, the carbon gases simulation, and the mercury simulation, as you see here. The full chemistry simulation, or what we call full chem, sometimes has several different options that you can pick from. Most users will use the standard option. GEOS-Chem support team uses the benchmark option to evaluate, to run simulations that we use to evaluate GEOS-Chem's performance. There are a couple of different SOA options and POA options. TOMAS and APM are aerosol microphysics, and RRTMG is the radiative transfer model that lets you archive radiative forcings from GEOS-Chem. Next, there are simulations that have been implemented without using KPP, such as the aerosols only, transport tracers, metals, and tagged ozone simulations. You'll find information about each of these at Read the Docs, as we looked at before. Some simulations, which are listed here, the standalone methane, standalone carbon dioxide, and the tagged carbon monoxide simulations, are deprecated. These are slated to be replaced by the carbon gases simulation, which now incorporates all of these species. So these individual simulations are slated to be removed from GEOS-Chem at a future point. And then also I'll lastly notice that the POPs simulation has been deprecated. It's stale, it needs some work. It was implemented many years ago, but then kind of fell out of use. So we need some work to recover it. So if you're interested in using the POP simulation, persistent organic pollutants, please contact the Mercury and POPs working group for more information about it. GEOS-Chem Classic has all of the typical atmospheric operations that you would expect. There's advection, or moving the species around by the winds, PBL mixing, computing PBL height and PBL mixing, computing dry deposition velocities, emission, PBL mixing, and then applying the emissions and dry dep fluxes, cloud convection, chemistry, and wet deposition. And these are executed in these routines that are listed here and at these locations in the code. So if you're interested in taking a look at the source code where these things happen, this is where they happen. And I won't go into the details, but if you're interested, go look at these routines and you can see how the code is laid out. One thing I do want to mention about KPP, because we mentioned that several of the GEOS-Chem simulations use code generated by it to implement the chemical mechanism. KPP is a separate package. The kinetic preprocessor, it's a separate tool that translates a chemical mechanism specification from text to optimized source code. So how it works is that you first lay out a chemical mechanism in text files, plain text. Then you run that through KPP, and then KPP will generate a bunch of Fortran codes, Fortran modules that we add into GEOS-Chem, and these Fortran modules accomplish the integration of the chemical mechanism forward in time. You can also run KPP in box model mode to test the mechanism, and also the KPP standalone code, standalone box model code, is now included in GEOS-Chem. And if you're interested in using KPP to change chemical mechanisms, I would look at this chapter, the Update Chemical Mechanism with KPP chapter of Read the Docs. So I'm not going to go into this in great detail, but this is what a snippet of a KPP chemical mechanism file looks like. So here you'll see that you have things that you would expect in a chemical mechanism, such as you have a list of species. Ignore here means that you're not going to do mass balance on these species. You're not going to have KPP perform any mass balance. Some of them are variable. The def-var means these are the ones that evolve with time. The fixed ones are the ones that don't evolve with time. Then there are your equations. So this is your chemical reaction. So things on the left in red here are your reagents. Things on the right here in green are the products. And, I missed a couple of colors there. I'm sorry about that. And the things here in blue are the rate constant. So a rate constant can be a mathematical expression, can actually be a function call, and it can also be an array or a variable. So KPP will take this specification and generate source code from it. GEOS-Chem Classic also has several ways that you can archive diagnostic quantities from it. And we have a whole section in the GEOS-Chem Read the Docs called Diagnostic Reference, but I'll just go over some of the important ones. So emissions diagnostics are handled by HEMCO, and we're going to talk about HEMCO in just a few minutes. So HEMCO has a separate run directory diagnostic configuration file, and you can specify which emissions you want to save out, how often you want to save them out, etc. And these are explained in this section of the Read the Docs in the HEMCO Read the Docs.io chapter there. Most GEOS-Chem diagnostics are implemented with what we call history diagnostics. So these are things like species, budgets, prod loss, production and loss, and so forth. And the configuration file for the history diagnostics is called history.rc. Both in GEOS-Chem Classic and in GCHP, it's called the same thing. And for more information, you can look at this chapter, the archive output with history diagnostics, in the GEOS-Chem readthedocs.io documentation. There are two specialty diagnostics. Plane flight diagnostics allows you to follow a plane, such as from an aircraft campaign. You can give it a list of coordinates that the plane flew in lat, lon, and pressure. It will save out GEOS-Chem concentrations or other diagnostic quantities along that flight track. So it's very useful for those of you who are looking into, for example, air quality or trying to compare model data versus aircraft data. Instead of having to save out a large amount of data, you can only save out data along the actual plane flight track. So for many of you, that might be an attractive option to use for diagnostics. We do have a separate chapter of that called Plane Flight Diagnostic. And then also NOAA has several OBSPAC observation stations around the globe. You can actually download an OBSPAC file in GEOS-Chem. OBSPAC Diagnostic will read the coordinates out of the file and save output at those station site coordinates. So if you're interested in using that, I would refer you to the OBSPAC Diagnostic documentation, which is also on GEOS-Chem readthedocs.io. And just to give you an idea of what the history diagnostics file looks like, here's a snippet of it. So this thing up here, the EXP ID or the experiment ID, basically doesn't change. So this is saying that the diagnostic files will have this prefix. So usually diagnostic files are saved to the output dir directory of the run directory, and they all start with GEOS-Chem. You can define one or more diagnostic collections. Here there are 3. Down here we're only showing 1 because of space. But each collection is essentially a different file that will get created. And in each collection, you can save one or more diagnostic quantities or diagnostic fields. Here is species comp, species concentrations in mixing ratio, species concentrations in number density, molecular number density. You can use wildcards in GEOS-Chem Classic. This refers to advected species. This refers to all species. So instead of having to type out each species individually, you can just use wildcards to subset a given group of species. And here you can also say how often you want data to be archived to the file and how often a new file should be written. In both cases, these are monthly. So you think about year, month, day, hour, minute, second. As I mentioned previously, GEOS-Chem Classic uses other software packages as submodules. The emissions package of GEOS-Chem is called HEMCO, the Harmonized Emissions Component. What is HEMCO? HEMCO is the emissions module of GEOS-Chem, as I just said. It reads native resolution emissions and other data and regrids them to the simulation grid. So you don't have to pre-process emissions. Whatever emissions they come in, as long as they're in a netCDF file, HEMCO can read and regrid that data to the GEOS-Chem grid or your simulation grid. HEMCO lets you define an emissions profile for your simulations by editing a single configuration file. So we take the complexity of making an emissions configuration out of code and into a single configuration file. So you tell HEMCO where the files are, how often you want to read them, which species to read, and so forth and so on, what scale factors to apply. And we'll take a look at that all in the next few slides. HEMCO also contains several extensions which compute emissions that depend on meteorology. So In many cases, your emissions are simple as just reading a file from disk, but if your emissions depend on meteorology like temperature, pressure, that comes from the parent model, which is in this case GEOS-Chem Classic, then HEMCO has some code to read the meteorology and to compute the emissions based on that meteorology, and we'll take a look at that later. HEMCO can also be run in standalone mode separately from GEOS-Chem, and this is very useful if you want to compute a long archive of emissions, but don't want to run that within a GEOS-Chem simulation that would take a longer time to execute. HEMCO has been interfaced to other models such as CESM and the NOAA UFS model separately from GEOS-Chem. HEMCO allows you to specify scale factors for emissions. So with HEMCO, you can take a global emissions inventory as is shown here. So in this case, this is global anthropogenic nitrogen oxide emissions. And then you can modify that. So without modifying the actual files, you can say, I want to take this code, I'm going to read in some scale factors, and I'm going to read in an annual scale factor to account for annual trends, and then we may have some seasonal trends, and then we may also have some weekday or weekend or hourly scale factors. So weekday, weekend could be important in urban areas, for example, where vehicle emissions are much less on weekends in some places than they are on the weekdays because of the commute. And so you take this file and multiply it by all these scale factors, and HEMCO will compute the total anthropogenic NO emissions for you. HEMCO also allows you to combine and overlay emissions by specifying a category and hierarchy for each entry. The category corresponds to the type of emissions, in other words, anthropogenic, biogenic, biomass, natural, etc. HEMCO also allows you to combine and overlay emissions by specifying a category and hierarchy for each entry. The category corresponds to the type of emissions, in other words, anthropogenic, biogenic, biomass, natural, etc. Emissions having different categories will be added together. So for example, anthropogenic NO plus biomass NO will be added together to make total NO. The hierarchy value specifies in which order emissions of a given category should be applied. In the example above, we have these global emissions, which are category 1 for anthropogenic and hierarchy 1, because hierarchy 1 is the base layer. And then we're going to overlay on these some regional emissions over the US and some regional emissions over Europe. So for the US, we give it a higher hierarchy value. We give it in case 10 instead of 1. And for Europe, we give it another higher hierarchy value, in this case 20 instead of 1. And when HEMCO goes to combine all these emissions, it'll say, okay, I'm going to start with the lowest hierarchy, which is the global emissions. And then when I get to North America, I see, oh, I have emissions with a higher hierarchy than the global emissions, so I'm going to overlay those on top of the global emissions. And when I get to Europe, I also have another hierarchy that's higher than the global emissions, so I'm going to overlay these European emissions on top. So the result is global emissions everywhere except over the US, where we have US emissions, and except over Europe, where we have European emissions. You can also specify a mask region for each regional inventory. A mask region is a binary mask that is either 0 or 1. If it's 1, you count the emissions within that area. So over here, the mass values would be 1, and outside the area, they would be 0, which means you don't count the emissions there. So here's a snippet of the HEMCO configuration file, which is called HEMCO_config.rc. So here's the entry name. For each entry, you specify the file where the emissions is to be read from. That's this edgar.nc. The variable from which to be read, that's the CH4 oil, CH4 gas, etc. The time period that you're going to read. So in other words, you're saying that the data exists between 2010 and 2022. That's what data is in the file. That there are months from 1 to 12, and the data is monthly mean, so you're going to read the data within this time period on the first day of the month at 0 UTC, and that you're going to cycle the data, which means that if you're outside of this time period, you're going to use the closest year. So that if you're using 2022, if you're in 2023, you'll use 2022. If you're in 2009, you use the year 2010. XY means it's two-dimensional. The units for most emissions that get read into HEMCO is kilogram meter squared per second, kilogram per meter squared per second, excuse me. We're going to read these emissions into the methane species CH4. Now, in some cases, you may have an emissions entry that needs to be multiplied by either a scale factor or a mask or both. So in this case, we're multiplying by these scale factors in blue. We're going to mask it so to only include the area of the continental United States, and we're going to specify the category and hierarchy. So this is now going to be, because we're masking this to the continental United States, this is now a regional inventory, so we need to give it a higher hierarchy than the global inventory here. So this will get overlaid on top of that, as we saw in the previous slide. And scale factors and mass are listed in the file below the section of where the emissions happen. For more information, we have a whole section in the HEMCO Read the Docs called More Configuration Examples that goes into much more detail. HEMCO also has a comprehensive diagnostic capability to archive emissions fluxes. So, for example, you can archive total emissions, as shown here. You can archive emissions over a single region like Europe or the United States, or you can just archive a sectoral emission, such as biomass burning or anthropogenic or what have you. So here's a snippet of the HEMCO_diagen.rc file, which is the HEMCO Diagnostics configuration file. So for each diagnostic, you'll list its name at the left and the long name at the right. So this will be the description that goes into the netcdf long name attribute. The species that you want to archive, the extension, category, and hierarchy. Now, base emissions, in other words, if you're just reading it from a file, base emissions are 0. If it's a HEMCO extension, you will list the extension number. A -1 means to sum over everything. So in this case, sum over, for total emissions, you want to sum over all extensions, all categories, all hierarchies. In other words, if it's not total, you're going to list specifically what category and hierarchy. In this case here, for total emissions of this category, we want to take all hierarchies. That means all, not only the global, but also regional inventories. So as I said, values of -1 will sum over all extensions or categories or hierarchies. And you should take a look and cross-check with the category and hierarchy in the HEMCO config.rc file, because that will, the categories and hierarchies that you list here should match what you have in the HEMCO config.rc file for specific diagnostics. Now, one of the things that you can use the HEMCO standalone for is to speed up GEOS-Chem simulation. So, for example, if your simulation reads a lot of emissions data from disk, you may want to consider pre-computing those emissions with the HEMCO standalone. So, for example, you can archive daily, monthly, etc. emissions fluxes with the HEMCO diagnostics from a standalone simulation. And then you modify your HEMCO configuration file in your GEOS-Chem run directory to read the pre-computed emission fluxes that you generated with the HEMCO standalone. The reason why you want to do this is because you only have to read the total emissions field for each species, because in netcdf, when you open a netcdf file, there's a lot of overhead in opening and reading, and HEMCO also has to regrid the data. So there's that data I/O is computationally intensive. So if your emissions configuration has a lot of files that need to be opened, what you want to do is consider pre-processing them with a HEMCO standalone simulation to get total emissions, then just read the total emissions into GEOS-Chem. That will make your GEOS-Chem simulation run much more efficiently. And we have information about using the HEMCO standalone at the HEMCO standalone guide at hemco.readthedocs.io. Okay, now I'd like to spend a few moments discussing how you can visualize the diagnostic outputs generated by GEOS-Chem and HEMCO. GEOS-Chem and HEMCO archive diagnostic outputs to netcdf files. These files contain not only the data, the diagnostic outputs from GEOS-Chem or HEMCO standalone, but also the metadata. Metadata is data that describes data, which is why it's called meta, or one higher than data. So for example, the netcdf Fortran interface provides several functions with which you can obtain information about the contents of a netcdf file before you even read the file, before you even read the data from the file. So you can get an idea of how large each field in the netcdf file is, what's contained in it, the units of the data, and so forth. All of that's stored in the netcdf file. In Python, there's a package called xarray that can read data from netcdf files into a consistent data structure. Not only does it read netcdf, it reads a few other file formats like HDF5 and ZAR and a couple other common ones. But the important thing is it puts it into a consistent data structure, or data structures. One's called data set, and another's called data array. A data array is like a field. A data set would be like a file type structure. That once you get it into these data structures, it makes it very easy to manipulate them in your Python scripts and Jupyter notebooks, which is great. And so we have built around xarray and other Python packages GCPy, which is the GEOS-Chem Python toolkit. And this is what we use, for example, to generate the benchmark output plots and tables that we use to evaluate how GEOS-Chem is performing. However, it also contains several visualizations and regridding routines for your convenience. So it's an easy way to plot data from GEOS-Chem or HEMCO. GCPy, the latest version of GCPy, which is at the time of this writing or the time of this video is 1.6.1, is now installable on PyPy or from PyPy, which is the Python package index with the pip installer. So if you run this command, pip install geoschem-gcpy, it will install GCPy to your computer. Now you might be wondering, why is it geoschem-gcpy and not GCPy? Well, it turns out Google stole the name GCPy. They have I forget what it is, but it's a Google package, so that forced us to pick geoschem-gcpy instead of GCPy, but that's a minor detail. And for those of you who are familiar with Anaconda, you can also install GCPy from the Conda Forge channel of Anaconda with either the Mamba or Conda installer. And this is another Conda or Anaconda and PyPy are the two main places where Python code can be downloaded from, and GCPy is on both of them. So again, I would point you to the installation instructions, GCPy read the docs.io, and we'll get our laser pointer back here, GCPy read the docs.io. So here, with xarray and GCPy, you can create scripts to visualize GEOS-Chem diagnostic output. And here's a simple example. It only takes 3 packages to do this, so that you have to import xarray, matplotlib, which is a standard plotting package in Python, and GCPy. In this case, we're importing one routine from GCPy called single panel, which is to plot a single panel. So the script basically does 3 things. So you read the data into an xarray data set with this command, the xarray open data set command. Then we're going to take the data, which is this object here. We're going to take the methane in mixing ratio units from it. We're going to slice it at the first level. We're going to take out the first level and the first time in the file, store it in this array. Now this is a data array object. This is a data set object. And then with single panel, we pass this data array object to it with a bunch of other configurations. Like we can give it a title, we can give it the color map, we can have some control over the color scale, we can crop it to a given domain, minimum max lon, minimum max lat, and then this is the matplotlib command to draw the image. And as you see on the next page, it will pop open a window on your screen with the plot. Now, you don't have to pop open a window to the screen every time. You can also tell single panel, say I want to save it to a PNG file or a JPEG file or a PDF file, and it will do that for you as well. So again, gcpi.readthedocs.io is your best documentation source for how to generate plots, and there's some examples listed there that you can take a look at. So this brings us more or less to the end of our tutorial. So if you have any questions, the best way to contact the support team is to open a new issue on GitHub at this link, github.com, GEOS-Chem without a dash, GEOS-Chem with a dash, issues, new, and choose. And I can show you that when we go to the our web browser. So I'm going to go to the next page here. So if you go to that link, that will put you on, let me just give me a second here. We want to go. And so that will bring you to this page, and it will ask you, do you want to make a bug report or an issue report, a feature request, a question or discussion, and also has a link to the user manual if you want to check that out first before opening your issue. And when you click on this, it will ask you to fill in your information, and we don't have to go through it because it's pretty much self-explanatory. So you'll put a title here, your name, what happened, how can we reproduce the bug, and some information about what you're using, and so which version you're using, which compiler you're using, etc., etc. So that's a really an important way that creating an issue is the best way to report problems, but also you can ask questions of us as well. So every issue is not just a bug report. Even if you just have a question about GEOS-Chem, you can pick the question or discussion issue, put your name, your affiliation, and just what your question is for us. So the reason why we like GitHub issues rather than email is because GitHub issues are transparent, they're searchable, and they won't get buried in your email inbox. Because we've had situations in the past where somebody has sent an email to like maybe one person on the support team, but that person was on vacation, and so they didn't see it for a while, and emails tend to get buried. And so by making a GitHub issue, all of us will see the issue when it pops open at once, and we can better respond to you. Also, I can go over a few features of the issue tracker before we end today. So, for example, if I open the issue tracker, it says there are 116 issues, and they're listed here. Each issue has a category and a topic. This allows you to filter issues. So, for example, if you're interested in all the bugs issues, you can click on bug, and so for example, you may find that someone else had the same problem with a particular version of GEOS-Chem. So if you click on bug, you can see if somebody reported it already, and so you can scroll through them and see if there was a solution for it. So these are the bugs that are open. If you click on close, these are bugs that have been, if it's a purple check mark, these are bugs that have been closed, probably because there's been a bug fix. So for example, you can see if you click on this one, you can see that, I've noted that we can close this issue because this pull request fixed it. So that means somebody submitted a fix to it that went in the model, so that we're able to close that issue out. And so, by clicking on any of these, you can get, I'll go back to the issues page here. If you want to find out about all the topics that, for example, like everything dealing with a configuration file, if you have a problem with one of your HEMCO or GEOS-Chem configuration files, you can click on the configuration files topic and filter it that way. You want to see all the feature requests, you can click on feature request and filter it that way, and so forth and so on. So it's a really powerful tool. And we ask you that before creating a new issue, take a quick moment and see if you can find if someone else had that issue before, because chances are there may be a fix for it. And if there's not a fix, please by all means open the issue. We'll be very happy to answer it, to talk with you about it. So that's all I have. I'm Bob Yantoska for the GEOS-Chem support team, and we'll see you in the next video.